Hello everyone. We want to talk about more chart types such as waterfall charts, dot charts, Gantt charts, histograms, and box plots in this lecture. We're going to learn about some basic and advanced chart types. We will talk about how these charts encode data and how they can be used. And we will see examples of waterfall charts, dot charts, Gantt charts, histograms, and finally box plots. Waterfall charts are used to visually illustrate how a starting value of something evolves to become a final value. For example, let's say a beginning monthly balance in our checking account undergoes some changes until it becomes the ending balance in that month. Waterfall charts use height and often color to encode data, showing increases and decreases between time periods or categories. They can effectively display the cumulative effect of sequential positive and negative values. Waterfall charts are commonly used in financial analysis to display how a net value is arrived at through gains and losses over time or between actual and budgeted amounts. The waterfall chart that I'm displaying here performs a profitability analysis for a product and its related services. 420K is the direct revenue from selling the product. 210K is the revenue for corresponding services of the product. Then we have two different costs. 170K are fixed costs and 140K are variable costs. And in the end, in total, we are up by 320K. So this line of product will end up being profitable. As you see, waterfall charts show a running total as values are added or subtracted. For example, here the running total is 630K, or here the running total is 460K, and here the running total is 320K. Okay. Dot charts can refer to a variety of charts. In the dot charts that we discuss here, data points are either vertically or horizontally illustrated with dot-like markers. Dot charts use position to encode data, and the position can be with respect to a common baseline. As you can see in these simplified dot charts, the dots kind of form a straight line. And we can have multiple of these if we have multiple variables. Now, let's see a small example. This table describes the number and types of pizzas ordered from a pizza store in a week. We want to draw a dot plot for this table. We choose our x-axis data to be the pizza type, bacon, cheese, and pepperoni. The y-axis, on the other hand, represents the number of orders received daily. As you can see, it sort of looks like a bar chart, but we are showing individual data points. Here is another example. This time the vertical axis represents different categories, meaning the shipment mode, and the horizontal axis contains the values, meaning sales for each shipment mode. We have also added some color encoding to represent the customer type, consisting of consumer clients, corporate clients, and home office clients. We can observe that for the first class shipment mode, the consumer clients generate the highest amount of sale, and for the same day shipment mode, corporate clients produce the highest amount of sales. Similarly, many other observations could be made. A variation of the dot chart applies a technique called jitter to offset the points so that they are not plotted on top of each other. The jitter is a random value, so we need to be careful not to jitter too much. A dot chart with jitter is also called a jitter chart. And if we have many categories of data, it will be called a strip plot or a strip chart. Let's look at an example. Here we have a dot plot with no jitter, which is hard to interpret. And here we have an equivalent dot plot with jitter. Now we have a better view of individual data points. So again, jitter is local displacement that's perpendicular to the scale in order to spread the dots and prevent the dots from overlapping and blocking each other. A Gantt chart, which is commonly used in project management, is one of the most popular and useful ways of showing tasks or events against time. Gantt charts use length and position to show when one task ends and another begins. This simple Gantt chart shows a car buying project. Task 1, we first do some research. We do online research. We ask our friends about their experiences, etc. We do this for almost a week, and then we start test driving select cars. We can actually do more research while we are test driving these cars, so these two tasks can partially overlap. Finally, we move forward with one seller and sign the paperwork to finalize the purchase. And we can put a vertical line through the Gantt chart to indicate the present time to see where we are with this project. The Gantt chart is arguably the most widely used project planning visualization. It is in fact the icon of project management. Let's now watch a video by Dr. Mike Clayton about the history of Gantt charts and more details on them.
The Gantt chart was invented by Karol Adamiecki. Karol Adamiecki invented his harmonograph 5 to 10 years before Henry Gantt went into print, describing what is now known as the Gantt chart. And there is absolutely no evidence that I am aware of saying whether Gantt was either aware or not aware of Adamiecki's work, but it does emphasize something important, which is that if you want something named after you, the best thing to do is to write about it in English, because that way Americans and British people understand what you're writing about. If you write about it in Russian, as Adamiecki did, then it might not get noticed and picked up. That's just the way the world worked in the early 20th century. Anyway, Henry Gantt gives us the rules that we use for creating a Gantt chart. A Gantt chart plots time along the horizontal axis. And on the vertical axis, we list all the tasks that need to be done to accomplish our project. And if you've created a work breakdown structure, then that immediately gives you your task list. And if you don't know what a work breakdown structure is, take a look at our video. What is a work breakdown structure? Now, once you've created your graph, and here's something important about the way Gantt charts work, equal units of distance along the horizontal axis represent equal units of time. Once you've created that, then you represent each activity by a bar. And the length of the bar represents the duration of the task. And the positioning of the bar represents the scheduling of the task. So if one task follows another, then the bar follows the previous bar. And so what we often see on our Gantt charts are these long diagonals of one activity following another in time, because each task is dependent upon the completion of the predecessor task to get started. But then we might have other work streams that run in parallel. The other commonly used symbol that you see on a Gantt chart is a simple geometrical shape like a triangle or a diamond that represents a milestone. And we have a video on what a milestone is as well. So, that's your basic Gantt chart. And it's very easy to read, and we can put a vertical line through the Gantt chart to indicate today. So that at any point in time during our project, we can read off where we should be in our project and then assess the level of completeness. Now, of course, when you look at real Gantt charts produced by sophisticated software, there are often different sorts of bars with different shading. There are sometimes different types of milestones, different shaped symbols. A milestone could be a decision point or a completion or a gateway review, for example. So how do you read these complicated Gantt charts? Well, my answer is it's simple. If you don't know what the symbols mean, that's not your fault. It's the fault of the person who created a Gantt chart. So when you create your Gantt charts, always be clear and put a key on the Gantt chart explaining what the different symbols and shadings and types of line mean, and that way your reader will be able to understand it very simply.
As you learned, Gantt charts are a powerful tool to help us think through our plan, to articulate it, to communicate it, and to monitor it. Now, let's talk about another type of chart. Histograms. A histogram uses height of bars to show the distribution of data. The bars in a histogram are plotted very close to each other and are not typically rotated, so they are usually vertical. Histogram charts are used to better understand how frequently or infrequently certain values occur in a given set of quantitative data. When we make a histogram, we group quantitative values by putting them into non-overlapping equal size intervals that are called bins. This process is actually called binning. We just need to have some quantitative data or variable to be able to produce a histogram. We do not need to have any categories or categorical variable. Here is an example of histogram of SAT scores of a group of 15 students. Let's see how it is constructed. Imagine these SAT scores for these 15 students are spaced out along a number line. In order to make a histogram, the number line is divided into equal chunks called bins. In this example, the number line is divided into 5 bins. Next, we count up how many data points sit inside each bin, and accordingly, we draw bars, one for each bin. The height of the bars corresponds to the number of data points in that bin. Of course, we draw a y-axis which counts the number of data points in each bin, and finally we label the bins. And we get this nice histogram to visualize the distribution of SAT scores for our students. Okay, let's now talk about another type of chart for visualizing the distribution of quantitative data. Box plots or box and whisker plots were invented by John Tukey, who is the father of exploratory data analysis. Box plots use position and height or length to show the distribution of the data. They also show min, max, median, and the variability of data at one glance. Again, a box plot is used to show a distribution of an entire set of quantitative data. That's the strength of the box plot, as it can summarize all of the data. It doesn't matter if it's 7 billion population of the planet or 10,000 attendees of a conference. It would be impossible to show those kinds of numbers with dots without significant overlap and a huge number of marks. The way that box plots work is that they aggregate and summarize the data. The box in the middle of a box plot represents the middle 50% of the data. The two ends of the box and the line in the middle of it mark the locations of three quartiles. So we have Q1, Q2, and Q3. Q1 or lower quartile is the median of the bottom half of the data. So 25% of the values are lower than Q1. Q3 or the upper quartile is the median of the top half of the data. The reason it's called the third quartile is because 3/4 of the data are below this number. And Q2 is the median of the data. So 50% of the entire data are below this number and 50% of the entire data are above this number. Whiskers are lines that are extending from the box, which indicate variability outside the upper and lower quartiles. The first and third quartiles give us information about the internal structure of our data, especially the part of the data that's centered around the median. The difference between the first and third quartiles is called the interquartile range, or IQR, and it shows how the data is arranged about the median. A small interquartile range indicates data that is clumped about the median, and a larger interquartile range shows the data that's more spread out. Lower whisker can be drawn down to the lowest observed point or min, and the upper whisker can be drawn up to the largest observed point or the max. And of course, we can have outliers and we can visualize them if we want. For example, we can have an outlier here. To understand the method behind constructing a box plot, imagine a set of 10 values that are spaced out along a number line. First, we draw a line at the median of the dataset, which is the value in the dataset that divides it evenly in half with an equal number of points smaller and larger. If there are an even number of points in the dataset, like in this dataset, what we do is we take the median as the halfway between the two central points. Next, we divide each half of the dataset in half, effectively dividing it into 4 even sets of points. The leftmost line marks Q1, the lower quartile, while the rightmost line marks Q3, or the upper or third quartile. Again, the median can be called Q2. Then we connect the lines that we have just drawn. So this box plot is starting to look more like a real box plot. Every box plot has lines at Q1, Q2, and Q3. The other major feature of a box plot is its whiskers, which can be drawn using a few different methods. One method to draw the whiskers is to first calculate the interquartile range, or IQR, which is the distance between Q1 and Q3, as we discussed a few slides ago. Next, we look at a subset of the data ranging between 1.5 times IQR below Q1 and 1.5 times IQR above Q3. Anything outside this range is called an outlier. So in this example, we only have one outlier, which is this data point. So the lower outliers are smaller than Q1 minus 1.5 times IQR, and the high outliers are greater than Q3 plus 1.5 times IQR. This is called the 1.5 times IQR rule for outliers. We then draw lines at the smallest and largest point within this range. Basically, we draw the lines all the way to the last value that isn't an outlier. Those lines define our whiskers. Usually showing every single data point would be distracting. So we just draw the outlier points. This is a common view for box plots. Even though most of the data points aren't drawn, we still know quite a bit about this data set. Okay, this was one method for drawing the whiskers. There is another method for drawing the whiskers where we say there is no outlier, all of the data points are legitimate, and in that case, we just draw one whisker at the smallest data point and another one over the largest data point. And this is what we get, which is another common view for box plots. Here I'm just showing the original data along with the two box plots for this data set that can be drawn using the two methods for drawing whiskers that we just described. Note that the boxes are the same, but for whiskers it is our choice how we want to draw them. We just went over two common methods, and there are in fact more methods to draw the whiskers. So far we have looked at box plots for a single series. Charts such as histograms give a more complete picture of a single series, but the real strength of a box plot is in comparing multiple series at a glance. This example shows the number of hours slept for each day of the week for a group of 20 high school students. Let's look at the medians first. Overall, the students sleep less and less as the week goes on, and they sleep more on the weekend. Now, let's try to analyze the boxes and whiskers. The boxes and whiskers show the same overall trend as the medians, but they contain much more information. For example, we observe that on weeknights, the boxes are not symmetrical. As you can see, the medians are very close to top of the box. Remember that in this region, there are the same number of data points or students as in this region, which is about 5 students. This means that the 5 students are more closely packed together in terms of their time slept in this upper region of the box. So the data is skewed toward this region. Let's make another observation. The large box on Saturday shows how inconsistent sleep habits are on Saturdays. The 10 students in the box, which represent the middle 2 quartiles of the data, sleep in a range that's about 3 hours wide. For days without outliers, the whiskers represent the minimum and maximum values. We see that students have relatively diverse sleep patterns, with the narrowest total range being on Wednesday for about 3 hours. And we can make more observations and gain more insights from this box plot. On a box plot, the outliers stand out and seem important. While they are sometimes interesting, remember that they are kept separate because they are different from the overall trend and shouldn't be used to make generalizations. In our sleep time dataset, the outliers only represent 4 out of 140 total data points. So it's okay to say one student barely slept on Friday night, but it's not okay to generalize and say on Fridays students barely sleep. Here are 2 more examples. This one compares the number of daily downloads of an app from January 2020 all the way to December 2020. We can observe an increasing trend followed by a slightly decreasing trend by looking at these boxes, which represent the middle 50% of the daily downloads in each month. The dots represent some outliers, and in some months we do not have any outliers. And this box plot compares the prices of books at two different bookstores, namely bookstore A and bookstore B. Again, remember that the box shows the range of the middle 50% of the data, and the line within the box is the median of the data. We can observe that at bookstore A, the prices of books are more spread out, whereas at bookstore B, the prices are clumped around the median. Another observation is the lower quartile at both bookstores. These lower quartiles are almost the same and they are equal to $75. But bookstore A has books that are as cheap as $65. However, the cheapest book at bookstore B is around $72. And many other observations can be made using these box plots without displaying every single data point. Okay, we will continue our discussion in the next lecture, going over scatter plots, maps, and tables.